Okay. Welcome everyone to today's CSC Knowledge Hub webinar. The title for the webinar today is Volcano Monitoring in the Eastern Caribbean, a Chronicle of Collaboration and Resilience. Before we begin, I'll introduce myself. So my name is Evangeline Arethuala, and I'm the Alumni Engagement Officer with the CSC Alumni team. And today I also have Today, we also have my colleague Kirsty Scott, who's joining the webinar, along with our webinar speaker, who I will introduce shortly. Our speaker today is Michal Camejo-Harry, who is a 2016 Commonwealth Split-Site Scholar from Trinidad and Tobago. She's a volcanologist and currently based at the University of West Indies Seismic Research Center, where she currently forms part of the scientific team responsible for monitoring volcanoes in the English-speaking islands of the Eastern Caribbean region. Michal specializes in volcano deformation and igneous petrology. I will leave Michal to explain to you more further in detail the webinar presentation and her expertise. Over to you, Michal.
Thanks very much, Evangeline, and thanks for giving me the opportunity to talk at your Knowledge Hub web series. So for the outline of my presentation, I'll start by giving you a brief overview of monitoring volcanic hazards in the Eastern Caribbean, where we have a multi-hazard environment. I'll then go on to speak about my role in volcano monitoring and research in this region. And then I'll finish off by giving you a brief case study of the recent eruption at La Soufrière volcano in St. Vincent. So the Caribbean region is made up of many small island developing states, and there are many challenges for these SIDS in the region. They have limited natural resources, they have fragile ecosystems, they're generally isolated from international markets, and in turn have limited internal markets. They have a heavy reliance on tourism and a heavy dependence on imports. On top of this, they are affected by multiple hazards with varied recurrence intervals and prediction capabilities. So we have hurricanes and tropical cyclones, which are an annual occurrence. Yet every year, hurricanes cause damage of about $835 million in losses. Climate change has exacerbated this by increasing the intensity and frequency of storms. In fact, the 2017 Hurricane Atlantic season was unprecedented with 10 hurricanes, 6 of which were categories 3, 4, 5, including 2 that were the most powerful ever recorded. And I show you an image here on the bottom right-hand side where you can see damage caused to the capital Roseau in Dominica from Hurricane Maria in 2017. There are also many other related hazards to tropical storms and hurricanes, such as flooding and landslides. However, these can occur just because of the rainy season that happens every year. We also have, because these islands are located close to tectonic plate boundaries, we have the occurrence of earthquakes and volcanic eruptions. Large magnitude eruptions and volcanic and earthquakes are comparatively infrequent occurrences, but when they do occur, the consequences can be equally devastating, if not more devastating. So we have this dichotomy between low frequency, high severity events combined with the annual occurrences of these regular hazards. And this is a major challenge that governments face in the region in terms of prioritizing resources for sustainable development. Like, how do you prioritize resources when you have hazards occurring every year, as opposed to large magnitude events that may not even happen in our lifetimes? However, we need to have a multi-hazard approach to disaster risk reduction that covers all areas of natural hazards and the interactions for effective risk reduction. And this is where my research comes in, trying to prioritize volcanic risk reduction for sustainable development. So why do we have volcanoes in the Caribbean region? Well, this is a direct result of our tectonic setting. So in this region, in the Eastern Caribbean, we have the collision of 2 tectonic plates, those are the North American and the Caribbean plates. And as these two plates collide, the heavier plate, which is the North American plate, sinks beneath the Caribbean plate in a process known as subduction, deep into the earth. And as it descends into the earth, the temperatures and pressures increase, causing this descending plate to melt. And this molten rock is less dense than the surrounding rock, so it then rises through the different layers of the overlying rocks, eventually erupting as volcanoes. So these volcanic islands that we see in the Eastern Caribbean are a direct result of multiple eruptions of one or more volcanoes over time. Now, the current active volcanic arc ranges from Grenada in the south to Saba in the north. And there are 21 live volcanoes spread over 11 islands, including the submarine Kikamjani volcano. Now, over the past 200 years, there have been over 30,000 people who have died in response to volcanic activity. So this is a significant threat that we face in this region. Many of these islands have one live or active volcano, but we have the special case of Dominica, which is thought to have 9 live volcanoes. So it's a more complicated history that we have in Dominica, and this has varied implications for disaster management, especially when you're going to consider all the other hazards that happen on an annual basis. These volcanoes tend to have 2 broad types of eruptive activity. They either erupt explosively or effusively. And I have some pictures here to show you what we mean by this. So explosive could be in the form of what you see in terms of typical ash clouds, and you also have pyroclastic flows. And effusive eruptions refer to a more calmer style of eruption where you form lava domes. Now, in this part of the world, the composition of the lavas that are produced are quite viscous and sticky. So when the lavas erupt, you don't get those runny lava flows that you would see, for example, in Hawaii and in Iceland. The viscous composition, the sticky composition, means that when the lavas erupt, they solidify near to the vents of the volcano and form domes. So subsequent eruptions form larger domes. And in many cases, once these domes grow rapidly, they can become unstable and collapse and form pyroclastic density currents. So these 2 broad types of eruptions have different implications and requirements for disaster management. In the Eastern Caribbean, the agency responsible for monitoring volcanoes in the English-speaking islands is the University of the West Indies Seismic Research Center, and we've been monitoring since 1953. Now, we are based in the island of Trinidad to the south, and we operate by being funded by 9 contributing governments. We operate a network of monitoring instruments, ground-based monitoring instruments in these islands. And this data is acquired and sent remotely to Trinidad, where processing and interpretation is done by scientists and technicians there. This is supplemented by routine visits to these islands for station maintenance and other types of data collection. We also work very closely within each national disaster office within these islands for disseminating hazard information. And we also contribute to the outreach campaigns to try and sensitize persons living there as to the potential hazards faced by volcanic eruptions. Now, anticipating volcanic eruptions is possible because as magma ascends, there are different surface manifestations. So the edifice may swell to accommodate this new magma making its way to the surface, and this is manifested in ground deformation. Also, as magma makes its way to the surface, the edifice may crack to accommodate this incoming magma, and this is manifested in volcanic earthquakes or seismicity. And this edifice cracking increases the permeability of the edifice, allowing for increased gas flux. So magma movement is usually accompanied by precursors, but this is not always the case. However, it is still important to have instruments to detect any of these changes to anticipate an eruption. Now, at the Seismic Research Center in the University of the West Indies, we use a number of monitoring techniques for monitoring volcanoes. We have a number of ground-based seismometers, which detect seismicity. We also monitor ground deformation using GPS. And more recently, with the advent of satellite technology, we also incorporate satellite monitoring to monitor ground deformation. Additionally, satellites can be used to map changes, topographic changes as a result of volcanic activity, also to map thermal anomalies and to track volcanic gases and ash from eruption plumes when volcanoes are erupting. We also do geochemical monitoring of the geothermal waters or hydrothermal waters and gases in volcanoes that have active hydrothermal systems. And this is done by, again, making yearly trips to these islands to take samples of these volcanic gases and waters. So we use all of this information to provide baseline data for assessing any changes in future volcanic activity. At the Seismic Research Center, I'm directly involved with ground deformation monitoring, and this is my current portfolio, GPS monitoring. Now, in this region, we have some challenges for eruption forecasting. So although we've been monitoring for a little under 70 years, you can imagine that this short time span is very short in terms of the life, the actual age of these volcanoes. These volcanoes are hundreds of millions to millions of years, hundreds of thousands to millions of years old. So therefore, this 70 years may not be an accurate representation of what these volcanoes are likely to do. Additionally, these volcanoes don't erupt very often. So on the right-hand side, you can see this figure where I've highlighted the number of eruptions that have occurred historically from the 18th century to present. The first thing that stands out is that not all of these volcanoes that we consider to be live have erupted within the last 300 to 400 years. And of those that have erupted, not all of them have erupted very often. Some of them have one eruption up to 14. So the historical record is very short. So we can just say, okay, well, since the historical record is very short, let's go back into geological time by doing field work to get an idea of what past eruptions may have looked like. We have some problems there in that some deposits may have been eroded. Additionally, dome-forming eruptions aren't always recorded or preserved in the geological record because they again may be eroded. And there's also a lack of fieldwork and dating in the region for past deposits. So all of these factors are challenges that we have to take into account when we're trying to forecast future activity. A complementary solution to this feature could be the incorporation of igneous petrology to try and image subvolcanic systems. So what is happening beneath the surface, beneath volcanoes, because the path that magma takes to the surface is poorly understood because we simply just can't see what's happening below the surface. Now you can use geophysical studies to try and get an idea of what the subsurface structure looks like, but these are generally very expensive, and so they don't happen very often. But we know that magma reservoir dynamics are a key contributor to volcanism. So we can use igneous petrology to try and image subvolcanic systems. Now we all may have in our minds from old textbooks what magma chambers or magma reservoirs may look like. So people may think you may have this large homogeneous body of completely molten material surrounded by country rock with a sharp transition between the two. However, over the past few decades, there's been an emerging paradigm shift in the scientific understanding of these systems from these classical magma chamber models to vertically extensive networks of crystalline mushes. So areas of mostly solid crystals, which you see in the stipple regions here, separated by small accumulations of melt in what we term a transcrustal magmatic system. So essentially, igneous processes are viewed as occurring throughout the crust, not just in upper magma reservoirs. And magma reservoirs really occupy the top part of a much larger transcrustal system. So processes in the larger system lead to magma accumulation in the shallow crust, and this corresponds to what kinds of features we would see at the surface in terms of activity. If we sample rock samples from different parts of this transcrustal magmatic system and do geochemical analyses on them, we can get an idea of the types of processes occurring at depth. And this is part of what I did for my PhD research. I went into the field and collected lava samples, which were erupted, and those really sample the melt-rich eruptible melt regions. And then in this region, you also have mushy crystalline regions also being erupted during volcanic events, which we term plutonic xenoliths. And the crystals contained in these rocks, which I've shown you here in thin sections, which are microscopic pictures of these rock samples, these crystals record the changing chemical conditions and thermal conditions where they would have resided before being erupted. So if we observe these crystals, they can place fundamental constraints on the processes operating within these magma reservoirs, and we can use this to figure out the architecture of these systems and what types of processes operate at depth. So for my PhD research, I studied 5 volcanic centers in the southern third of the Los Angeles arc between St. Vincent and Grenada. These islands are in the Grenadines archipelago. So I studied Bequia, Petit St. Vincent, Ile de Ronde, and 2 submarine volcanoes, Kikimjeni and Kikimjack. All of the field work was conducted in the Caribbean. And later on, after acquiring the SPECSITE scholarship, I was able to go to the University of Bristol and analyze all of these rock samples in the UK. And I should note here that without this Commonwealth scholarship, I would not have been able to complete my PhD research because we don't, in the Caribbean region, we don't have these facilities available. This was a great way for me to be able to complete my research. So at the University of Bristol, I studied the textures and compositions of these rocks and was able to reconstruct each magmatic system. And just to give you an idea of the output of some of my research, my PhD research, we were able to develop a model for what we think Kikimjeni, which is a submarine volcano, what its subvolcanic system looks like based on using rock samples erupted from this volcano collected during a research cruise. Now, this is the most historically active volcano in the region, meaning it has had the highest number of eruptions during historical time. And this model was generated after doing petrological analyses and also incorporating it with monitoring data. And we plan to use this model to try and interpret future seismic signals and to help with mitigating volcanic hazards at future eruptive events. So I'd like to go on now to talk about the recent eruption that started last year, December last year, at La Soufrière volcano in St. Vincent. This picture shows you an image that I took in February of this year, where I was deployed to St. Vincent as part of the scientific team monitoring the volcano. And at first glance, the volcano actually looks very peaceful in this picture, except for a few clouds above it. But at this time, the volcano was actually actively erupting. And one indicator of that would be the brown discoloration that we see on the edifice of the volcano. And this was a direct result of corrosion from the volcanic gases emanating from the growing volcanic dome. So I'll just give you a brief overview of La Soufrière's eruptive history. Within historical time, there has been about 7 eruptions, documented eruptions before the most recent one, and they have shown varied styles of activity. Sometimes they show discrete explosive or effusive activity. However, there have also been instances where they've had a combination of the two, specifically in 1979, where the eruption started off explosively and ended with the formation of a dome. So this picture shows you what the edifice, the crater of the volcano would have looked like before the recent eruption. So we have this 1979 dome, a product of the last eruption, and a small crater lake. And I should note here that because of the COVID-19 pandemic, the ground-based monitoring network was not to its optimum capacity because we were restricted in travel. So we weren't able to do the usual station upgrades and maintenance that were required to monitor the volcano adequately. So before this eruption started, there was only one seismic network, one seismometer, and one continuously operating GPS instrument working at the volcano. And because of this, we were not able to detect any precursory activity related to the start of this eruption. However, using satellite imagery, satellite data, we were able to detect a thermal anomaly on the 27th of December over the volcano's summit. This prompted us to contact the local National Disaster Office, the Soufrière Monitoring Unit, to determine whether or not this thermal anomaly had manifested with any surface expression. When they made an attempt to check, they determined on the 29th of December that there was indeed a dome growing right next to the 1979 dome. So this here shows you the start of an eruption. This dome represents magma extruding out to the surface, which represents an eruption. In response to this, the Seismic Research Center deployed a small scientific team to St. Vincent to immediately densify the monitoring network. So the map on the bottom left-hand side shows you how we densify the network to include more seismic stations and continuously operating seismic stations. And I show you here the location of the observatory, the Belmont Volcano Observatory, in relation to La Soufrière volcano. These images, these pictures just show you our attempts to increase the number of stations at the volcano, including installing cameras to remotely have close range views of the growing volcanic dome, and doing gas monitoring and installing new seismic stations, and doing campaign GPS occupations. I also show you an image here of a video that I took hiking up the volcano, just to highlight the fact that in this part of the world, when we do scientific campaigns, or we try to identify the network, in many instances, it requires us to hike up to the volcano. Helicopter support is usually very expensive, so this is not always available. So when I was there in February of this year, we had to hike up, and in many cases, we're hiking up with equipment, and depending on which side of the volcano that you hike up from, it can take 2 to 4 hours hiking one way. Just to give you an idea of the type of strenuous activity that is involved with monitoring volcanoes, and you have to have some level of fitness to get the job done. We were also very much interested in tracking how the dome grew from the start of the eruption. So we used a number of techniques to do this. We combined satellite radar as well as routine drone surveys to track the dome growth. And the image in the middle actually shows you the dome footprints that were calculated by a scientist who used these two techniques. So the different colored polygons just show you how the dome growth progressed over time between December 2020 and April 2021. This is just over 3 months of eruptive dome growth. However, the main indication that this was about to change was from the seismic data. So we had these various monitoring techniques, monitoring different aspects of the volcano, but the only indication that this was about to change from dome growth to something else came from the seismicity. Based on this information, the scientific team on the ground at the time recommended to the local authorities that an explosive eruption would have been imminent, and they recommended that things be put in place to have an evacuation as soon as possible. So I show you on the left-hand side here a hazard map that was produced before the eruptive event, showing you the different hazards faced to communities living at various distances from the volcano summit. So the volcanoes to the north, and you see the red, orange, yellow, and green zones. So upon recommendation to the government decided, based on our scientific advice, to evacuate persons from the red and the orange zones. And 24 hours later, after the start of the evacuation, the explosive phase of this eruption actually started on the 9th of April. So this is a prime example of a successful forecast where we were able to give the government 24 hours notice before an impending eruption. Now, this does not always happen, but in this case, it was a successful forecast. And the first few days of the explosions were actually they were full of a lot of ash in the atmosphere. So we can see this top left-hand picture shows you the view from the Belmont Volcano Observatory. Now, usually without ash obscuring the vision, you can see the volcano clearly from the observatory, but you can see how the ash would have put a damper on this, and we see some of the disruption of the ash would have caused. We see how the communities would have been having to adapt to having ash nearby. Also, this eruption didn't only affect St. Vincent and the Grenadines. The ash had far-reaching impacts, and actually, within the first 3 days of the eruptive activity, ash affected neighboring islands such as St. Lucia and Barbados to the east, and actually Barbados had significantly devastating effects in terms of the ash affecting the air traffic and affecting people's lives. And here I should mention they would have had to have been collaboration with air traffic control and meteorological agencies to assist with this response. Now, I mentioned that the ash from the explosive eruptions would have affected the scientific view of a volcano. Additionally, once the explosions had started, we would have lost some stations that were seismic and GPS stations that were on the volcano summit and the camera due to the pyroclastic flows. So through international collaboration, we were able to gain access to satellite radar imagery, which assisted us with viewing the volcano, even though we couldn't see it on the ground. So I give you some examples of what this would have looked like. So we see a picture here in the top left of the configuration of the volcano summit before the explosive phase. So we see the 2021 dome growing right next to the 1979 dome. And then after the explosions, which happened on April 9th, on April 10th, we see the configuration of the volcano changed. The domes that were there were blown off due to the energy caused by the explosive eruptions, allowing for open venting. And as the days progressed, we see subsequent infilling of ash material and then blowing off of material as the explosions progress. So this international collaboration really helped us to get an idea of what was actually going on at the volcano edifice, because we couldn't see and we had no instruments to detect it. In terms of some of the eruption impacts on the communities and on the environment, we can see that the weight of the ash would have felled some trees and also buildings, and also would have affected agriculture. We can contrast this figure that we have of the volcano with the earlier photograph that I would have shown. So we see that the volcano flanks are littered with ash compared to the green vegetation that we would have seen earlier on. And then the subsequent pyroclastic flows would have also deposited a lot of material along the flanks and towards the sea of the volcano. So this top right-hand image here shows you some people. You might be able to make out some people standing up on what is now risen landmass. So the beach would have initially been lower down, but subsequent pyroclastic flows and lahar deposits would have increased the height of the landmass. This eruption, even though it resulted in no deaths due to a successful evacuation, it is estimated to have costed 50% of the nation's GDP for recovery. So now, since the explosions would have stopped on April 22nd, we are now in a road to recovery. So since then, the alert level was dropped from red to orange, and we've now been deploying scientific teams to try and reestablish those monitoring stations that would have been lost during the explosive phases. But as I mentioned earlier in the presentation, we live in a multi-hazard environment. So because we are now in the rainy season and hurricane season, in addition to volcanic hazards, we now have a secondary hazard resulting as a result of rainfall. So when heavy rains fall, it mobilizes the ash deposited on the flanks of the volcano, causing lahars or mud flows. So this is another hazard that has to be incorporated with management strategies for the island of St. Vincent. So in terms of building back better, I hope I've shown you that a better understanding of natural hazards can assist with risk mitigation. And you can't have sustainable development without incorporating disaster risk reduction. Integrating geohazard research and monitoring with sustainable development is necessary to build internal capacities at the country level. And although we have many uncertainties associated with natural hazards, if we have suitable preparation, this can help to curtail economic losses in some ways and also prevent deaths. So the establishment of early warning systems really helps to manage residual risks. And this is a perfect example of how scientific monitoring helped with successful evacuations and response during this event. And it's really a lesson for many of the other islands in the region who have not had volcanic eruptions in recent times to learn from what needs to be done to prepare for future events. So I'd like to end here and thank you for your attention. And I'll now invite any questions that you may have.
Thank you so much, Michal, for this wonderful, brilliant presentation. on your work as a volcanologist, and also for shedding light on your involvement in the recently erupted volcano, and giving us your experiences on being a Commonwealth scholar, and how this has helped you in conducting your PhD research. So yeah, thank you once again for your presentation. We will now begin the Q&A session. So I would like to invite our attendees to send in your questions using the chat function. Equally, if you are studying or conducting research in this field, if you'd like to share your experiences, please let me know in the chat function, or if you have any questions for the speaker, please send in your questions. We do have a couple of questions that came in advance to the presentation. So Michal, if you're ready, I am just going to put forward a few questions to you.
Sure, yes.
Great. We have a question on from one of the registered attendees, and the question is, do volcanoes differ in their natural behavior patterns in different parts of the world? How does a volcanic eruption help the Earth?
Okay, so for the first part of that question, yes, the behavior of volcanoes differ depending on your tectonic setting. So as I mentioned in the beginning of the presentation, the volcanoes in the Eastern Caribbean result from a subduction zone setting, a collision setting, but you also have other settings, such as in Iceland, where you have diverging tectonic plates or ridges, mid-Atlantic ridges, and also in Hawaii, where you have a hotspot. So it all depends on the tectonic setting and the composition of the magmas, which determine what types of eruptive activity that you would tend to have. For the second part of the question, how do volcanic eruptions benefit us, I think it was. Volcanoes actually, the eruptive material actually provides fertile soils once they become eroded, once the ash becomes eroded, and it allows agriculture to flourish. And we have seen that in St. Vincent, where agriculture was a major part of the economy before the eruption. Also, young volcanoes can also be a source of geothermal energy, and that is currently being pursued in the Eastern Caribbean. There are many attempts underway to try and harness geothermal energy. And also in older volcanic centers that are now extinct, larger volcanic centers, you can also use, these volcanic centers will have minerals such as copper, zinc, that you would use in many manufacturing and technology industries for mining and so on. But that is not really relevant for the Eastern Caribbean, but it is relevant in other parts of the world.
Thank you for responding to that question. The next question is around flexibility and adaptability. So how do we enhance the ability of social institutions to adapt to change when a volcano erupts?
Okay, so I think what we try to do at the Seismic Research Center is try to develop long-lasting relationships with the local national disaster offices. As I mentioned earlier, we have a unique situation in this region. Many people are surprised when they hear that the volcano observatory is not actually located on the island. Everything is done remotely in most cases. But that really works because we have developed these long-lasting relationships with the local authorities, where we go there every year to conduct education and outreach campaigns. So we have that long-lasting relationship, and also we are heavily involved with educating younger children, primary school, secondary school children, to sensitize them to the variety of hazards that will affect them, volcanic and seismic hazards, so that education is being built from the youngest level, with the hope that it will be transferred to their parents, and it will develop this culture of being aware of the hazard environment. And in fact, St. Vincent was one of those islands where we had one of those well-established relationships already. We had a number of projects that were implemented within the last couple of years before this eruption that were focused on building community-based resilience. One notable example is the Volcano Ready Communities Project, funded by the Caribbean Development Bank, which would have resulted in a number of targeting 12 communities around the volcano to try and sensitize them and prepare them for any impending eruption. And of course, this eruption would have been a test as to whether or not those attempts would have worked. And in this case, people were willing to evacuate for the most part. So I would say the project would have been successful. But all in all, I think flexibility and adaptability to change really requires you to have that special, that partnership between the agency, the monitoring agency, and the local communities.
No, that's a very good insight that you have provided on the question. Thank you. We do have a couple of more questions coming in. So the next question is around climate change. So how do you relate climate change and volcano phenomenon?
Well, in most cases, the reason why volcanoes erupt aren't necessarily related to climate change. It's more because of tectonic processes. But climate change can exacerbate the effects of eruption. So we've seen in the case of St. Vincent, because we have all this increased rainfall, because the hurricanes seasons are becoming more intense and hurricanes are becoming more frequent, it has exacerbated the frequency of these secondary hazards associated with volcanic eruptions. And also, I'm not sure if people know, but volcanic eruptions can also in turn contribute to climatic changes, even though on a small scale, because they emit different gases into the environment. And I think in the past, in historical times, there would have been examples, or even before, there would have been examples of volcanic eruptions actually changing the climate for short periods of time, because the erupted gases and ash would have prevented sunlight from coming into the atmosphere and causing the entire global climate to change. So I think it affects both ways. Volcanoes can affect climate, and in turn, climate can affect the volcanic hazards.
Okay. Our next question is from Dolapo. I hope I'm pronouncing your name correctly. They are asking, first of all, they're saying thank you so much for your presentation. Their question is, could you please explain some sustainable alternatives to building back more resilient communities?
Okay, so, well, I'll use the example of St. Vincent. So as I would have mentioned, before this recent eruption, the last eruption was in 1979. And we would have hoped that local authorities would have learned from that experience to try and not build settlements in certain regions that would be affected by volcanic activity. However, we would have noted that many communities would have still lived in river valleys along the flanks of the volcano, because the soil is fertile there. They can do the agriculture, so the benefits outweigh the risks. But we're hoping from this experience, where we've seen that most of the devastation would have occurred in the northern zone, in the red zone, people who would have been living within riverbeds, their homes are now perpetually being affected by lahars or mud flows. That in this case, there will be greater government intervention in how communities are rebuilt in those regions. So maybe there can be campaigns to perhaps not build within river valleys, or perhaps limit building within river valleys, and maybe just live further away but conduct your work near to the volcano. And also in this region, we have to balance the fact that we have more than one hazard affecting us. So what may work in terms of building structures for having resilience to earthquake hazards or meteorological hazards may not be the same for volcanic hazards. And we see with the ash, when ash falls on buildings and it gets very wet, it actually becomes like wet cement and becomes very heavy and falls down. However, having a roof built in a particular way may be actually good for meteorological hazards. So we need to find that balance, and there needs to be, scientific intervention from all sides to try and figure out what is the best strategy for building communities in those regions. And I think putting those investments in now, even though it may seem to be very expensive in the short term, we will see in the longer term. And for St. Vincent, the longer term may not be too far away. This eruption happened 40 years ago. It's happened 40 years after the last eruption. And we've seen based on the number of eruptions in historical times, that repose interval between eruptions is actually getting shorter. So we need to actually start putting things in place now to build back better.
Thank you for highlighting, the need for balance. I think one of my questions around that is also if you have ever faced any challenges while working with partners in your field.
Do you mean colleagues within my agency or international?
With collaborations with institutions or organizations while you're monitoring.
So actually, for the most part, for this particular event, when the eruption started, we actually were happy to get this overwhelming scientific response from the international communities to assist us with this event. It was a true international and regional collaboration. So for the most part, it was very helpful to get this external insight in terms of trying to figure out how the volcano is likely to behave, getting the satellite imagery to help us to monitor the progress of the eruption. But also, in some ways, because we are a small scientific team, it was often very difficult to manage responding to the eruption and also having to manage all of the international partners who were trying to help. There were some challenges in finding that balance. So what we did at the agency was try to designate one point person who could be a sort of liaison between the international community and us local scientists, because we had the scientists trying to focus on monitoring, and they didn't really have time to be checking emails to see who said this, who said what, who's willing to share this. So that one person who was that liaison really helped with disseminating the relevant information from those international partners to the local agency to try and help manage the event. Generally, we tend to have a good scientific relationship with international partners, and that is how we've been, conducting our affairs for the past 70 years.
Thank you so much for responding to that question, Michal. I have a question from Madhu. I'm not sure if Madhu wants to unmute themselves and ask the question. If not, I'm happy to ask the question for you. Hi, Madhu. Should I ask you a question? All right. I'll just ask the question. Their question is, is there any pre-natural indicators to detect for volcano eruption to the country with limited resources of monitoring volcano eruptions?
Generally, when you start to see, well, in my experience, my limited experience, when you start to see manifestations that can be detected by human activity, is probably by humans, you're generally at a state where things are getting pretty bad. So when you start to feel volcanic earthquakes, it's probably that we already reach a point where something may be happening. It's generally best, if possible, to have ground-based instruments. I understand that many countries may not be able to afford to have monitoring networks, but monitoring networks actually detect activity that cannot be felt or observed by humans. And once they start to be felt and observed by humans, we are actually reaching a point where things are quite critical. But yes, I mean, in some cases, there are some periods within La Soufrière's volcanic history where you had over a year of earthquakes preceding an eruptive event. So you know something is about to happen, but you can't tell when. But people are actually feeling earthquakes. The problem with that is that without the ground-based instruments, you're not able to get a good idea of when an impending event is going to happen. But those are ways that you can tell just by seeing surface activity. But usually it's recommended that if possible at all, there needs to be priority in putting an instrument network in place. Also, as I would have mentioned in the presentation, not all volcanic eruptions are preceded by precursory activity. So you may have ground-based instruments, and then it picks up nothing. And then a volcano that has been silent or dormant for many, many years just erupts without notice. That does happen, but it's usually better to have the ground-based instruments because in most cases, you're able to pick up precursory activity. And also satellite, now with satellite imagery, through collaboration, even if you can't have, an agency can't afford a dense network of instruments, in some cases, satellites can pick up, as we saw for last year, for instance, Vincent, can pick up small changes in thermal anomalies.
Yeah, thank you so much for answering that question. Let me know if you need a break, Michal. We do have a few more questions to go. The next question is by Mohammed Faisal, and I think they would like to unmute themselves and ask the question. So Faisal, do you want to go ahead with your question?
Yeah, thank you so much, Eva, for giving me the opportunity. And thank you, Michal, for such a great presentation. My question is, I would like to ask, can you share some insight on volcano eruption in South Asia, any incident? And if there's any, when it was last time, and what was the level of physical and economic damage? Just a brief insight on the incident, please, if you can.
So did you say South Asia?
Yeah.
I wouldn't be able to share. I'm not familiar with any activity in South Asia. I wouldn't be able to share specifically because, well, that's not necessarily my area of expertise. So unfortunately, I wouldn't be able to share any details on any eruptive activity there.
Okay, no worry. Thank you so much. Thank you.
Okay, thank you.
Thank you so much.
Thank you so much, Faisal, for your question. Once again, if we do have any attendees from South Asia or any other region who have experience of working within this area, please do feel free to share your experiences. Equally, you can also share your thoughts or provide your experiences on your work in post-webinar discussions that will take place on the Knowledge Hub after the webinar. Thank you so much, Faisal, once again for your question. A last question from Tanay, who's asking about the losses. What about the losses associated with having your work close to an active volcano? There's another question, a follow-up question after that, which is, for farming, would it not be okay to move nutrient-rich soil to other zones to conduct your work? So there are two questions here, Michal, for you.
Okay, yeah, the first question, yes, there are extreme economic losses with volcanic eruptions, and we noticed that firsthand at St. Vincent. So when the explosive phase started, we had a number of monitoring instruments near the summit of the volcano. Seismic instruments and GPS instruments are very expensive, and we would have lost, we lost at least one GPS station and 2 seismic stations at the, and including a camera. Of course, it takes money to try and replace all of these instruments. So yes, it's expensive, and this was because of this, we tried to supplement the losses by using satellite imagery where possible in some cases. But generally, monitoring networks are very expensive to maintain. But in most cases, when you install them, once the eruption happens, they tend to last for quite a number of years once you have routine station maintenance. The second question was about moving fertile soils from volcanoes to other areas for agriculture. Now, I'm not an expert on agricultural activities, but I would imagine that moving soils, freshly erupted soils, I don't think that when volcanoes erupt, the soils are immediately able to be used in farming. It needs to be weathered to some degree before it can be beneficial for agricultural soils. In its raw state after being erupted, it's quite acidic. So I'm not sure that things can be used for agriculture straight away. But I suppose moving soil from one place to another becomes a logistical issue, depending on the persons living on the ground, the local authorities for what works for them. But in many of the islands in the Eastern Caribbean, they are entirely volcanic. So even though, for example, in St. Vincent, the eruption would have occurred in the north of the island, The rest of the island is made up of older volcanoes that are no longer actively extinct. So generally, the soils in St. Vincent probably have a great level of fertility anyway. So
yeah, thank you so much, Michal, for responding that. I think that was a really good response in terms of the question around the soil and soil fertility. Okay, so with that, we have come to the end of our Q&A session. We do not have any further questions in the chat function. But as I mentioned, we will have post-webinar discussions on the Knowledge Hub, strengthening resilience and response to crisis. Michal is a member of the Knowledge Hub, so please do get in touch with her if you have any questions for Michal. Michal, thank you so much for your presentation once again. And as I said, it was really enlightening to know about the volcano eruption and specifically in terms of the Eastern Caribbean region. So yeah, thank you so much for your presentation. Thank you so much for everyone who attended this webinar. As mentioned, this webinar is being recorded and the recording will be shared on the CSC's YouTube channel shortly. Yeah, as mentioned, please do get in touch with us or Michal directly on LinkedIn on the Knowledge Hub if you have any questions for her. Thank you so much once again. Everyone, thank you for attending this webinar.